Now let's look at why the moon has exactly the same angular size in the sky that the sun does. That means that the moon exactly covers the sun during a total solar eclipse. People think this is kind of weird and it must have some basis in something, or like double rainbow, what does it mean, and all that kind of stuff. But what it really means is a confluence of factors that began with how the moon was formed, the fact that the moon is tidally locked to the Earth, and that the moon's orbit has changed over time. So let's look at all of those things, because right now we know from Apollo missions, the mirrors left on the moon, that the moon is drifting away about 1.5 inches further every year. That's really interesting. So let's look at what this all means and how it relates to why it's the same size. So let's start with the formation of the moon. The giant impact hypothesis, which is depicted here, suggests that the moon was formed from the ejecta of some collision between the early Earth and some Mars-sized planet approximately 4.5 billion years ago. And that would be roughly about 20 to 100 million years after the solar system formed. The object that hit the Earth so long ago has been informally named Theia. Why? Because in ancient Greek mythology, Theia is one of the 12 Titans, who are the children of the Earth goddess Gaia and the sky god Uranus. Her brother consort, and this is kind of what the thing that kind of makes people go about it, is Hyperion, a Titan also, and a god of the sun. And together they're the parents of the sun, the moon, and the dawn, Helios, Selene, and Eos. And Hyperion is, just like Theia, hardly ever comes up in the mythology of the Greeks, and Theia is mostly important for the children that she bore, Selene, Eos, and Helios. That just means that the only thing you ever really hear about her is that she's at least the goddess of sight and vision, and had endowed gold, silver, and gems with their brilliance and value. Which is actually pretty interesting, considering that when a massive collision like this occurred, the heavy elements such as gold and silver sank to the center of the Earth, and very few of them went into the moon. Anyway, so this giant impact hypothesis is currently the favored hypothesis for the formation of the moon, and there's a lot of evidence that supports this hypothesis. The first is the moon's orbit has the same orientation a similar orientation to the Earth's spin. The Earth's rotation axis and the moon's orbital axis are very closely aligned. They only differ by a little bit. The moon and Earth system also contains a huge amount of angular momentum. And this angular momentum is tied up in the Earth's rotation, the moon's rotation, and the moon revolving around the Earth. This is the sum of these things is significantly higher than the other terrestrial planets, Mercury, Venus, and Mars. And a giant impact would have definitively supplied this excess momentum, or it could have. The moon has a small iron core, and this gives the moon a lower density overall than the Earth, and computer models show that a giant impact of a Mars-sized body with the Earth would seem to make the impactor's core penetrate all the way into the Earth and fuse with the Earth's core. That would leave the moon, which was formed from the ejecta that we see here, that would be from the surface level stuff, like the less metallic iron, because the Earth at this time had already partly stratified, meaning iron had sunk to the core, and less heavy materials were at the surface, such as silicates and so on. Furthermore, there is evidence from star systems other than the solar system where we see evidence of collisions that would result in debris disks. Here we see one of the earliest that was ever found. This is the star Beta Pictoris. Beta Pictoris is in the dead center of this image. There's an exoplanet, Beta Pictoris b. That blue occultation image is because that's an image from the Very Large Array. But the infrared image goes up and to the left and down and to the right. That's European Southern Observatory Adonis instrument. But what we're really caring about there is not the exoplanet in the center, which is really cool, but really the dusty disk that is occurring in the upper left and lower right that surrounds the star Beta Pictoris. Debris disks would occur if there were major impacts, and Giant collisions are very much consistent with the leading theory of the formation of the solar system, and such debris disks are found around other stars, so we do believe that this is the case. Next, the Apollo moon samples showed that stable isotope ratios of the lunar and terrestrial rocks, the rocks from the moon and the rocks from the Earth, they're identical, and that implies a common origin. Also, the Apollo moon samples indicate that the moon was once molten to a great depth, and this would have required a huge amount of energy than would be predicted from available if you just had an accretion of the body from the moon size. If just it came together under gravity inside its own dust, inside that dusty disk that we saw around Beta Pictoris. Now, in order to make it much more molten quite deeply, an extremely energetic process, but such as a giant impact, could provide that energy. Next, the moon is depleted of volatile elements compared to the Earth. Volatile elements vaporize at comparatively low temperatures, and they'd be lost in some high energy event. With the moon's smaller gravity, would not be able to recapture them, but the Earth would. That means you need to have some extraordinarily hot environment, and an impact would provide that. And this image is from December 13th of 1972, and this is Harrison Schmitt from Apollo 17 taking such lunar samples during their second extravehicular activity on the moon. So yes, the moon was actually visited by people. Isn't that wonderful? Let's assume that it has been, that the moon was created in a giant impact. Fantastic. Now that means that the moon and the Earth are orbiting each other, and they pull each other gravitationally. And as they pull each other, they orbit each other, but there's also, because they're going around in little circles around the center of mass, actually more like an ellipse, but let's keep it a circle for ease here. As they go around that center of mass, as we just showed, the red arrows, so we have these two dots, the moon would be on the bigger circle because it's swinging around, and the Earth would be on the smaller circle because it's the more massive body, so it would be closer to the center of mass. The gravitational attraction between them would be the same, and that's the red arrow and the green arrow. And the centrifugal acceleration, so gravitational acceleration is red, the centrifugal acceleration is green. And these things are balanced in this system. Otherwise, if they weren't balanced, then they would be they would either be falling together or flying apart. And part of that centrifugal acceleration, in fact, the centrifugal acceleration, is due to the fact that they're orbiting a center of mass. If they were not orbiting a center of mass, there would be no centrifugal acceleration. So that's what the white arrows were indicating, and that's what I showed with this thing before. So the X marks the spot of the center of mass. And so now when we've seen that, we can say, fine, we have actually not just point masses, but they're distributed objects. And this is an important thing. So now we've got a big Earth on the left and a smaller moon on the right. Remember again that in a rotating reference frame, we have to remember this is a rotating reference frame. I'm not going to show that rotation from this point onward, but I wanted to show you that from that diagram before that we're really acting in a rotating reference frame, and we have to take care of both the gravitational acceleration red and the green centrifugal acceleration, which is due solely to the fact that they're in a rotating reference frame. So we've done this. Let's remove the orbital parameters and separate out those white arrows just so we have clarity, so we know what we're looking at. And now that we're in the rotating reference frame, rotating along with the moon and Earth as they go around their orbit, that center of mass, we then say the next thing, which is, what's it like when we isolate just the surface bits when we want to see the effect of the moon on the surface bits of the Earth? Strictly speaking, because we're looking at centers of mass, we really should be looking at every little bit of the Earth, from the nearest to the farthest, all the way through the core, everywhere in the entire Earth. But that would make a really messy diagram, and I don't want to do that. I want to actually be clear, so I'm just going to look at the surface bits, but we have to remember that the tidal interaction from the moon on the Earth is going to be due to all of the parts of it. But I'm just going to choose a series of lines. But first, what I'm going to do is say for each of those lines is affected by the same centrifugal acceleration. And this is true If we ignore the Earth's rotation, this is a good approximation if we ignore the Earth's rotation. If we added in the Earth's rotation, then we would just have some flattening of the Earth that we would have to take care of. But really, we think about the experience of centrifugal acceleration at that point in that rotating reference frame. So what do we mean? They're always pointing in the same direction. So I just want to help you with that. What I mean, why I can say that all of these green arrows are the same. It's because in a rotating reference frame, they're all going to rotate around their own center of mass. So let's see what that kind of looks like. Each of those green arrows is staying with respect to each other as they orbit the center of mass. When you have a distributed system that's orbiting that does not rotate, each point is rotating around its own circle in order to maintain the non-rotation of the Earth. And that's what we just saw. So those red arrows showed that the green arrows, these red arrows, which are not gravitational, these red arrows show the difference between the center of mass for the surface bit and the center of mass of the entire system. And they're the same because they're going around a circle that has the same diameter at the same speed. The centrifugal acceleration field that is experienced at the surface of the Earth due to the rotating reference frame can be shown to be the same for every point on Earth in diagrams such as these. Let's get back to this original thing where we have centrifugal acceleration inside this rotating reference frame. And now what we're going to do is we have to take the center of mass, the red arrow in the Earth, and apply each of its bits per bit. So that's what we're going to do next. So what I did is I removed the center of mass of the Earth and put the yellow arrows on each of the lines that says each bit of the Earth here is feeling a gravitational acceleration towards the center of mass of the moon over on the right. And so we have two arrows at each point, one centrifugal, which is green, and one gravitational acceleration, which is yellow. The yellow ones differ from the green ones because some points on Earth in this distribution are closer to the moon and some are farther. If they're farther, the arrow will be shorter. If they're nearer, the arrow will be larger. If they're off axis, they'll have to point towards it, so they'll kind of swing down a little bit. And so if like at the very top, the yellow arrow is bent very much down compared to the green arrow. But in the near side, at like say 3 o'clock, the yellow arrow is exactly the opposite direction as the green arrow, but it's longer, so therefore the gravitational acceleration is greater. But at 9 o'clock, the centrifugal acceleration is greater than the gravitational acceleration. All of these things added together would make the red arrow we saw on the previous slide. Okay, so let's get rid of the lines just to make it a little easier to see. Now I'm going to add the two arrows together. If I vector added the green and the yellow one together, I get the little blue ones. And these are the net acceleration inside of this rotating reference frame at that point on the surface of Earth. So this is a vector addition, so the green arrow plus the yellow arrow equals the blue arrow for each one of them. This is vector addition. And so we're left with these. We really don't have the other two things because their net effect is the blue arrow. And now let's look at all of the arrows on that surface, every single one. And now let's dim things down so we can see it a little easier. And now we're left with the familiar tidal bulges. They arise because of the differential gravitational field between the moon and the Earth inside of a freely falling two-body system in a rotating reference frame. That's important enough to say it again. The tidal bulges arise from the differential gravitational field between the Earth and the moon, where you look at the points on the surface of Earth and every point on Earth as it's getting pulled on the moon compared to its centrifugal acceleration away from the center of mass inside this freely falling two-body system in a rotating reference frame. These tidal bulges would not happen if the moon and Earth were not orbiting each other. They simply would not happen. So now let's draw a line between their centers of mass to get some sort of distance indicator. And now let's remember that the Earth is actually rotating. And because the Earth is actually rotating, this rotation drags the oceans ahead of the true line between the centers of mass. So that tidal bulge is not pointed always at the moon. It's ahead of that. And why? because the Earth is rotating faster than the moon is orbiting. So when that happens, the friction between the Earth and the oceans drags that forward. The flexing of the Earth is not really too huge, but the oceans are the significant thing that is taken into account. But that wave takes time to process, and the rotation drags it forward very quickly, so that bulge points off axis. As a result of this misalignment of these two lines, that creates a torque. And that torque imparts angular momentum into the moon's orbit, which speeds it up, and therefore it falls away from the Earth and it grows distance with time. And the Earth's rotation slows. Let's say that again. The reason that the moon's orbit is changing is because there's a torque between the line of the bulges of the tides that's dragged forward by the Earth's rotation compared to the center of mass between the Earth and moon. And that creates a torque, and that torque slows down the Earth and speeds up the moon and makes the moon drift away. And over time, this happens. It gets farther and farther away. After its formation, when the moon was formed, it was very, very, very close. It might have been, say, 15,000 miles away or so. Only a few Earth radii away from the surface of the Earth. And today, as a result of this tidal interaction, 4.5 billion years later, they're now separated by 240,000 miles, which is about 385,000 kilometers. And the Earth is spinning slower, much slower than the time of the moon's formation, and the moon is much further away than the time of the moon's formation. And the moon took a very short period of time to tidally slow down to have the same rotation period as its orbital period. That happened inside of 4.5 billion years for the moon, because the moon's a smaller body. And so the torque that it would have had on due to its rotation, and that would have back reacted, of course, on the Earth as well, that would have spun, that would also serve to push them apart. So the moon now faces the same way as the Earth. I just ignored everything that I did with the Earth. I ignored that for the moon for this diagram. But it did happen on the moon as well. And that's why we see only one side of the moon. So due to tidal acceleration, therefore, the orbit of the moon becomes about 3.8 centimeters more distant every year. And that's about the same rate that your fingernails grow. That also means that the average solar day, which is defined to be 86,400 equal seconds, is getting longer by 2.4 milliseconds per century when measured in standard SI units with respect to atomic clocks. So the atomic clock second is different than the mean solar day second, and by 2.4 milliseconds per century. This small difference accumulates over time and has accumulated to the point where in 1972 the world adopted the leap second in order to compensate for differences in this time base for these two standardizations. Thinking about the Earth's rotational slowdown, how long will that take? Well, we can predict what it'll be and how far away it'll be. Eventually, the Earth will slow down until the rotational period of the Earth is 47 Earth days. And at that time, the Earth would face, only one side would ever see the moon. Just in the same way, if you're on the moon, only one side can see the Earth. But models that predict this predict that it'll take about 50 billion years, 50, not 5, not 15, 50 billion years to achieve that. That's too slow. That's really too slow, because in a 1.5 or about a billion years from now, a billion and a half years from now, the sun, whose radiation is increasing, and it will increase to the point where water will not be able to exist on the surface of Earth, and all the Earth's oceans will boil away. That'll reduce the tidal interaction. But even without this slowdown cannot be completed in 4.5 billion years, which is when the sun is expected to grow into a red giant, destroy the Earth and moon. So the Earth will never, ever, ever get to that point, and the sun will die before the Earth slows down to that point. So let's see what that looks like in a separate diagram. So right now, The Earth is about, well, right now, the Earth is about 8,000 miles wide, about 12,700 kilometers. And let's see how that looks with respect to the Moon's orbit. The Moon is about 2,000 miles across, or about 3,500 kilometers, and its distance is about 385,000 kilometers. So there's the current Moon orbit. The current Moon orbit is about 240,000 miles. It's really tiny compared to the other orbit, and that's why we don't see lunar and solar eclipses all the time, because it's far, and it's a very tiny target. But at this distance from the Earth to the Moon, that means that the Moon, given that the Moon is 2,150 miles across and about 240,000 miles away, that means the Moon is about a half a degree in the sky. Now the Sun is very, very large, and it's 150 million kilometers away. So therefore, it's about a half a degree in the sky. That's the current orbit. It's just grown to that place. In earlier times, the Moon would have been larger. How much larger? Here we go. At the time of the Moon's formation, 4.5 billion years ago, the distance would have only been about 24,000 kilometers, or about just under 4 Earth radii away. That's really close, 15,000 miles away. That's super close. At that distance, when the Moon was formed, it was about 8.5 degrees in the sky, or 8.3 degrees in the sky. This is enormously close. Now, the Earth was spinning a lot faster, and the Moon was going around quickly, and the month was a lot shorter. This was a whole ball of wax. It was a really crazy time. And well, after the formation, the Earth did not look like this. It just was a hot, glowing, molten thing, and so was the Moon. But let's see what that might have looked like. Let's pretend. So let's go today. Here is an image that looks over Europe, taken as an AP photo by Petros Giannakouros. And in this image, we see a full moon rising in the east, and that's quite beautiful. And it's looking over a hillside in Europe. It looks absolutely gorgeous. And in this image, the moon is 1/2 a degree. So whatever the size scale of this image that we're seeing, the moon is 1/2 a degree. What would this image look like 4.5 billion years ago? Well, it kind of would look like this. This is really kind of scary. The moon would look this big in the sky. It would be about 16 times larger in the sky. And of course, this is Photoshopped. Of course, this is not a real image of the moon. I've just Photoshopped this. I even made the background look terrible just to make it so it's obvious it's Photoshopped. Anyway, when the moon was this close, there would be no annular eclipses because the moon is much bigger in the sky than the sun. The sun would still be 1/2 a degree in the sky, but now the moon is 8.5 degrees in the sky. It's huge. There would also likely be very few full moons that weren't in partial eclipse. There will always be a full moon, but when it's in full moon, there would always be a partial eclipse. Why? Because the moon's orbit is inclined only 5 degrees with respect to the Earth's orbit around the sun, but the angular size of the moon is 8 degrees. So at the farthest it could be is 1 degree outside of dead center, and the Earth's shadow is still pretty big. So we would always see 4.5 billion years ago some sort of partially lunar eclipse. And you would almost always get solar eclipses, where the moon would go in front of the sun and completely block out the light to the Earth. That's amazing. That would happen all the time. Eclipses back at the moon's formation, total solar eclipses would happen all the time. But you wouldn't see the corona like we do. Why? Because it's 8 degrees in the sky, and the sun is 1/2 a degree in the sky, and the corona only makes it at most a degree in the sky. So this combination of the moon moving about 1.5 inches further every year led us to be able to have eclipses. All the kinds of diversity of eclipses that we know it's a temporary phenomenon. Now we've always had them. They've always been solar eclipses, but the moon's angular size has been shrinking over time. And during human evolution, during the time of Homo sapiens on Earth, the moon's size has been roughly this. So many of the archaeoastronomy sites that have been found across the world, which can be, many of them are World Heritage sites, they describe how ancient cultures were really trying to understand the motion of the sun and the moon. Hundreds of millions of years in the past, the moon was closer, and therefore larger, so every total solar eclipse, well, it was either total or partial, and there were no annular eclipses. That would be hundreds of millions of years in the past. Due to this tidal acceleration, we now have annular eclipses because sometimes the moon is closer in its orbit and sometimes further. And millions of years in the future, the moon will be too far away to finally completely cover the sun, and there will no longer be total solar eclipses. And in that same time frame, though, the sun is going to become brighter, and so it'll appear to be larger in size. And when will this happen? When will we get the last eclipse? The estimates are somewhere between 650 million and 1.5 billion years in the future. That's going to happen way long time in the future. So there's nothing to say, oh my goodness, humanity is going to see the last of this. Well, if humanity manages to live to 650 million years and be that successful of a species, good on humanity, because that would be amazing. But we don't have to worry about that today. We don't have to worry about not ever seeing an eclipse. They're just relatively rare. So let's circle back to the original question that I posed at the beginning of this video. Why? Why exactly does the moon cover the sun almost perfectly during a total solar eclipse? And in fact, today it can. It can be an annular eclipse that's a little too far away, or it can be a total solar eclipse where it's closer and it totally covers the sun by more than a little bit. But is there some great cosmic significance that says that the moon is this distance and the sun is that distance and they're both the same angular size in the sky? No, you could assign some sort of purpose to it, and that's what people typically think when they think why. This video was more about how. Why? You know, the why meaning how does this happen? How did it happen such that today we see that? It's just a confluence of events. It's not like we were put on Earth yesterday and this was created for us. No, eclipses happen for many planets in exoplanets all across the entire universe. In fact, we discover exoplanets by them passing in front of the stars and creating partial eclipses of those stars. That's how the Kepler Space Telescope found many of them, by these tiny little partial eclipses of distant stars that it can see. And so, you know, and if you were on Jupiter, there's so many moons, you'd have all sorts of little eclipses. And so what we look at is that there's no religious significance. There's no purpose for a total solar eclipse. So when we say why exactly? Well, it's just that time in geologic history where it is doing that. It won't do that in the distant future, and it was slightly different in the past. It's just that the moon is slowly moving away, and as it does so, it gets smaller and smaller and smaller in the sky because its angular size is getting smaller and smaller in the sky. That's what we mean. It's physically not getting smaller. It's just moving away, so it looks smaller. That's why. That's all. It's not super significant in that way. However, it is emotionally significant. It is a beautiful thing. And if you do get a chance to go see a total solar eclipse, you must go see one. It's really exciting to see the stars come out, to see the ring of sunset all around you. And I wouldn't trade it for the world. I went to Glendale, Wyoming, and this is a picture of me with my parents. And it's just an amazing thing. I would not trade it for anything. And in fact, you should make sure you get in there too, because the visceral feeling that you get during that is so significant that I can't imagine that these events did not have significant impact on human feelings and evolution over the last tens of millions of years. Maybe even, and I'm just speculating here, totally speculating, that solar eclipses had an influence on our thinking with respect to religion and the bases for it and why there's lunar calendars throughout many religions. It could just be that solar eclipses were such significant events that they helped create the need for cosmology, the needs for religion. Amazing. But, that's total speculation, and I'm sure there'd be a lot of people who would really disagree with me on this, and that's okay. I'm not holding fast to that idea.